Hello, this is Mr. Yontz. We're going to begin our programming course. We're going to use the book Introduction to Java Programming AP Edition by Y. Daniel Liang. I've searched many years for an ideal textbook, and each time I find a new one, it gets closer to that, and I think this one is the best so far. We're going to discuss not so much programming in this course as problem solving using programming as a tool, the emphasis being on the problem solving. Of course, we're going to be using computing devices. We call them computers. Many things have computers these days, other than personal computers, many things. Now, of all existing problems in the universe, only a small number of them can actually be solved on a computer. It may sound surprising, but there's quite a few that cannot. If we represent our universe as this huge rectangle, that's everything in the universe, then there's this subset of things, entities, ideas called problems. Not everything in the universe is a problem, though there are a great many problems. And by the way, if I can use mathematical terminology notation, I will. Programming deals with problem solving. Problem solving often has a numerical element, even if it's not solved on a computer. So math is very important. Get comfortable with notation and concepts. Okay, in this subset of problems, there's a number of them that are solvable in what we call algorithmic, with algorithmic solutions. That is a step-by-step process. So I'll call that subset A. Not all problems are algorithmic, but a great many are. For example, baking a cake. There's a certain sequence of steps you have to go through to do it. Otherwise, you'll mess the cake up. You can't just do it any old way. Changing a tire on a car is algorithmic. There's a certain set of steps you have to go through to do it effectively and correctly. We care about that. In our problem solving, we can only solve problems that are algorithmic in nature. Computer is a machine that does a step-by-step process, just like any other machine, and therefore it has to have a sequence of steps to follow to solve problems. So obviously they have to be algorithmic. Now within algorithmic problems, there's a subset that we'll call C for computational problems. Not every algorithmic problem is computational in nature. For example, the cake and the changing the tire. Certainly you could get robots to do it, but the problem you're actually solving with the robots is how to get them to do steps using computational ideas whose end result would be things like mixing dry ingredients for a cake or removing lug nuts for a tire. But the real problem you'd be solving would be the computational aspects of getting those done. So we're going to narrow our concerns to computational problems. Not every problem is inherently computational, but if we can encode it into a computational form, we can use computers to solve it generally. Now, I'm going to show you an aside here. I love doing asides just to give additional information. Within computational problems, there's two additional sets, and I'm going to draw first off three possibilities, and then I'm going to, inside the computational, I'm going to draw the one I think is correct, although I cannot prove it. There's two sets of problems, NP and P. Now, these are computer science terms, and NP stands for non-deterministic polynomial time problems. That's a lot of gobbledygook to say, basically, we don't know how to solve them, or we can't solve them in a reasonable amount of time. P are polynomial time problems. We know how to solve them, and we can use computers to do so effectively. This is a possibility that no NP problem is a P problem. Now, computer scientists who are typically very math heavy work on this problem. It's unresolved. It's one of the top unresolved computer science problems. We don't know the relationship between NP and P. There's another possibility, is that all NP problems are actually P problems. We just don't know it yet. We haven't been able to determine mathematically their structure, etc., and solve them. Now, these are two possibilities. There's one other possibility that I will draw in here, and this is the one I think is true, but it's only my gut feel, my intuition. There are some NP problems that are actually P problems. We just haven't gotten the math down yet. When we do, it'll be okay. We'll be able to turn those NPs into Ps and solve them. So, in a sense, what I'm saying is what we're dealing with is a very limited set of possibilities of all things that we could solve. And on a computer, even if they're algorithmic and computational in nature, not all of them are practical. So think of NP and P not in their true terms, but as not practical and practical. We're going to focus on practical, computational, algorithmic problems. And that's what programming for us is going to be all about. How to solve problems using a computer. And they're going to be practical problems in the sense that we can actually solve them on the computer. All right. Many as of yet unsolved problems can be encoded into computer terms and solved using computing devices. That's kind of your task, is to take things that may appear to be non-computer based and put them in terms that a computer can handle and then solve them. That's really your task. That's what you have to train your mind to do. Computer science and computer scientists who are heavily mathematical, they focus on what's possible. And if possible to solve, can it be done efficiently? Some problems can be solved on a computer, but it's going to take billions of years to do so. That's not considered practical. You as a programmer are going to focus on solving practical problems by implementing a specific algorithm. The algorithm is what the human mind is going to come up with. It's going to solve it with those steps and use a programming language to tell the computer what to do to solve the problem. An algorithm is an ordered set of necessary steps. You've got to have all the steps in place. It says it should be minimal. That means don't add extra steps that are not necessary. It may not prevent the problem from being solved, but it's not helpful either. And oddly enough, an algorithm needs to be guaranteed to terminate. Part of those NP, or not practical problems, is some solutions never finish. They go on forever. That's not very practical. So we need to make sure that our solutions return an answer in a reasonable amount of time. Now, here's another limit of a computer and computing problems. Machines only understand numbers. Technically, they only understand whole numbers, 0 through 255 decimal. That's all the numbers that you can encode in a byte. Everything else is a combination and reinterpretation of those tiny integers. That seems like a huge limitation, and in some senses it is. But the craft of programming and problem solving is figuring out how to convert problems that are not inherently integer based, small integer based, into those small integers and reinterpret them into something meaningful that actually turns out to be a solution to a huge problem. Machines understand numbers. Humans don't tend to deal well with numbers, but we do understand symbols. We use concepts like big, sunny, bright, pretty, small. Those don't have precise meanings, but they mean something in relation to other things. And those are symbols. We write languages. We have letters and words that don't have inherent meaning, but we interpret them a certain way and we communicate. Machines are not good at that. So there's a mismatch between us humans and those computers. And programming is the art and science of instructing the computer how to solve problems using symbolic language, which computers don't understand. So we have tools called interpreters and compilers that convert human thinking into machine thinking. And we will talk about that later. So a program gets translated into native machine language. That is something the machine understands. A list of numbers. That's all it is. All program ultimately is a list of numbers that the computer understands. And once the computer has that list of numbers to work on, it does so very rapidly. Magic. Oddly, a computer can perform only a very small set of operations on data. I've worked with some that only have a dozen or so operations. That's it. That's all they do. But one thing to be sure, computers perform operations extremely precisely. They always do it the same way every time. No matter what the data is they're working on, they're going to do the same steps and they're going to do it accurately. Something we humans don't do with numbers too well. I'm terrible at symbolic manipulation, algebra, that stuff. I always mix up my signs or I do a division wrong or something. I'm just really imprecise. Not a computer. They're unearthly precise and fast. Now, when a problem can be encoded into machine concepts, the sheer speed and precision of the computer makes it appear like magic. Think of a video game where a character is interacting with an environment. Maybe it's a first-person shooter. Somebody at a distance is, shooting bullets. Or you make your character dodge to the left and hide behind a tree. And the tree has branches with frilly leaves or fronds on it or something. And you see all these colors and textures and sounds, and the terrain changes and you have to go around things. And after a while, the mind just accepts this as a reality. I've known people who have done flight simulators and they begin to lose control of the plane and their heart rate goes up. They sweat. They feel tense. Well, nothing's happening. Just a bunch of numbers are being processed, and those numbers translate into pixels and sounds and all. But that's all that's happening. But the mind accepts it as real. There's a magic that occurs. And the computer, when well programmed, seems to be magic. It's not. It's pure math, but the mind accepts it as something amazing and wonderful. And so I'd like to welcome you to the wizarding world of computer programming, because it's the place where you make that magic happen.